Okay, so today the question I would like to address in these next lectures are the large deviations. So what we have seen is that if we define the empirical measure pi and t, and we have some dynamics, let's say the exclusion which we defined and worked with in these last lectures. So what we proved is that pi and t follow the solution of some differential equation. So that we could write as dx, d rho, dx rho, with some boundary condition, initial condition. So that is to say that if we start with some measure mu n, which is associated to this density profile rho 0, and if we fix a time interval 0t, then pi and t will be close to rho t x dx in this time interval. So for, let's say, that if I look what is the probability that pi and t is close to rho t x dx for t between 0 and t, that this will converge to 1. And what would I say here? By this statement, what I want is, let's say, that I fix a delta positive, and I'm asking what is the probability that the supremum for t between 0, remember that I have a distance which is the distance which gives rise to the weak topology, then that pi and t rho tx dx, that this is, let's say, larger than delta, and what we know is that this is converging to 1, to 0, for all positive delta and for all t. Okay? This is essentially what we proved. So now the question I would like to address is, well, let's take a trajectory u tx, which is different from this solution. Okay? So you take something, and by a trajectory, what I'm thinking is that for each t, I have ut, which is a density profile. So for each t, I have ut, which is a function from the torus to 0, 1. So I'm thinking that this has a trajectory in time. And my question is, well, what is the probability that starting from mu n, that instead of having that this supremum, so that pi and t actually follows this trajectory ut x dx. Okay? Or that this is or maybe let me put it as less spherical than delta. So I'm taking a tube around utx, ut. So at each time t I have ut, I look at a neighborhood of ut of size delta. So I have a tube, and I'm asking what's the probability that pi n will belong to this tube. I know that if ut is different from rho, then that probability goes to 0, because, well, pi follows rho, which is the solution. So I know that this goes to 0, but I would like to estimate this probability. Okay? And so what we will prove is that this is equal, in some sense, to the exponential minus n I0t of u. So there is a functional which will be called the rate functional of the large deviation principle, which measure what is this probability. So this is, and then there is an error in delta. But what I'm saying is that if I take this limit first in n, so what I will do, we have exponential, so I'll take the logarithm of that. I'll divide that by 1 over n. And what I will say is that when I do that, I take the limit in n, and then the limit in delta. This will converge to a functional. So this is the more or less what I would like to do. Okay, and so this is large deviations. And in order to explain the techniques in large deviation, I would like first to address a simpler question, which is the large deviations of IID random variables. Okay? So I'll explain how to derive the large deviations for IID random variables. Then we'll see what is the strategy, and we will adapt the strategy to the context of exclusion process. So today, I would like to address the large deviations of IID random variables. And to fix idea, so I'll consider maybe the Bernoulli random variables to be in the simplest possible context. So I have a sequence xj, j larger than 1, and these variables are IID, and let's say that the probability that xj is equal to 1, this is 1 minus the probability that xj is equal to 0, and maybe let me call that alpha. Okay. So this is what, these are my assumptions. So you know the law of large numbers. If I take n of these variables and I take the average, then these converge in probability or almost surely to alpha. Okay. So in this sense, what I have is that this probability that xn bar minus alpha, that this is larger than delta, that this will converge to 0 for all delta. And this is what I called xn bar. Okay. So this is exactly the law of large numbers in probability. Right? For all delta, this converges to 0. And so the analogous question here is, well, what would be the probability that xn bar is close to some beta? So it belongs to beta minus delta, beta plus delta. That will be exactly the similar question, the analogous question. So we know that if delta is small and beta is different from alpha, this goes to 0. We would like to show that actually this is exponentially small. Okay. So what we will prove? We will prove an upper bound and a lower bound. The upper bound, which I state, is that if I take for any f, so xn bar takes value in 0, 1. Okay, these are values which takes value 0, 1. So xn bar belongs to 0, 1. So I will restrict my values beta in 0, 1. And what I'm saying is that for all, what I will prove is that for all f in this interval 0, 1, which is closed, then the following holds. If I take the probability that xn bar belongs to f, so you can think that f is this set closed, okay, the closed interval. If I take the log of that, so log 1 over n, and if I take the limit sup of this, so this is equal to minus the infimum for all alpha or for all beta in f of I of beta. So I'll prove that there exists a functional I, and this functional will appear naturally in the proof, for which this is holds. Okay. So I will be a functional from 0, 1 to R plus, which will be lower semi-continuous and convex. And we will prove a lower bound that for all G in 0, 1 open, then the limit imp of 1 over n log the probability that xn bar belongs to G, that this is larger than minus the infimum for beta in G of I of beta. Okay. So this, and this means that if you take a set A, and like this set or any set, what is, and you want to estimate what is the probability that xn bar belongs to this set A, you have an upper bound saying that the probability that xn bar belongs to A, it's less than the probability that xn bar belongs to the closure of A, and then you can use this estimate. So here you'll get the closure of your set, and you have a lower bound, which is the probability that xn bar belongs to A. It's larger or equal than the probability that xn bar belongs to the interior of A, which is an open set, and then you can use this lower bound. So we will have in this way an upper bound and a lower bound for the probability that you're looking at. Right? Okay, so this is what I'm going to prove, this upper bound and lower bound. And what I want to show you is that actually the strategy that we will follow in order to prove these two bounds will be exactly the same that we will adopt in the Markovian context, or in the context of the exclusion process. Right? So let's start with the upper bound. So I want to estimate the probability that xn bar belongs to F. Okay. So what I will do is I'll define this as the probability that xn bar belongs to F. And here I will introduce an exponential which makes xn bar appearing. So let me call Sn the sum of xj. So that xn bar is Sn divided by n. Okay. So I want, I'll take here Sn theta. Okay, so I'll just introduce this term. I want to make this object mean 1. So what is the expectation of E theta Sn? So this is, Sn is the sum, so this is a product of E. They are all II, so they are IID, so this is exponential of theta x1. So this is actually the expectation of theta x1 to the power n. Okay, so let me call maybe m of theta the exponential of E theta x1. So m it's a, yeah? No, it's not an inequality. Sorry, it's an inequality. Sorry. Thank you. No, I'll prove an upper bound and a lower bound. Sorry. So let's go back here. So let me define this function m of theta to be this exponential, this expectation of this exponential, so that this is m theta to the power n. Okay? So this is my computation. So this exponential, it's mt to the power n. So I wanted this expression to be this expectation to be 1. In order to get this expectation to be 1, I have to divide that by this object, or taking this is n log m of theta. Okay? So this object here, it's positive and has expectation equal to 1. Right? For any theta. For any theta, this expression has, so let me maybe keep the definition of m. And let me erase. So what I did is I multiply this expression by this, and I divide it. All right? Okay. So now mind. I can rewrite. So this term, I will keep it. Let me look at this one. This one, I will write it as n times theta xn bar minus log of m of theta. Okay, I'm just putting the n as a factor. And now, mind, I know that xn bar belongs to f. So this expression, it's less or equal that here I will just take a supremum over all beta belonging to f. So this is less or equal than supremum over all beta in f of this quantity minus n beta minus minus theta beta log of m of theta. Yeah. Xn bar belongs to f. So this expression here, since xn bar belongs to f, it's bounded by the supremum over all beta in f of this expression. And I have an incorrect, and there's a minus sign here, theta. Okay. Okay? I'm just replacing bounding xn bar by the supremum of all possible values. And now you notice that, well, this does not depend anymore on xn. So it gets out, it's a constant, it gets out from the expectation. Okay? Gets out from the expectation. Now, this is the indicator of a set, so it's bounded by 1. So let me bound this expression by 1. And I keep this one, but this one, you have seen that I defined m for this exponential to have mean 1, which means that all this term is bounded by this exponential, and I forgot the n, right? There's a minus n and the supremum. Okay, so all this expectation is bounded by this exponential of this supremum. So, with this trick of, so what is important here? It's important that I introduced a functional of xn bar. So this object, it's a functional of xn bar, which is positive and has mean 1. It was important to be a function of xn bar because I took here the supremum over all possible values of xn bar. If this expression was not a function of xn bar, I couldn't have done that. So here I need a functional of xn bar, and I need it to be positive and mean equal to 1. And if I have that, I can get this bound. So what we proved is that the probability that xn bar belongs to f, it's less or equal than the exponential of what's written there. So exponential supremum. So let me exchange the minus sign with the supremum and n. So minus n. And when I exchange the minus with the supremum becomes an inf. Inf beta in f of theta beta minus log m of theta. Is this what we have over there? Okay. Which means that now, if I go back to my bound, if I take the logarithm, I divide that by n, 1 over n log of the probability that xn bar belongs to f, that this is bounded by minus the infimum over beta in f of theta beta minus log m of theta. Okay. Mind that the right-hand side does not depend on n. So I can take the limit sup. It's still bounded. And the left-hand side does not depend on theta. Okay. So I can optimize. So this bound is true for any theta. Okay. So I can optimize over theta. So by optimizing over theta, I'll take an infimum over theta, but with this minus, I get a supremum. So this is bounded minus the supremum over theta, the infimum over beta in f, theta beta minus log m theta. Okay, so in 5 lines, you get a bound. And now if you compare this bound with the one I promised, well, you see that there is this theta. So here you need an argument to exchange this supremum with this infimum. So here, and what's going on? What I claim is that this function, log m theta, it's a convex function. I'll show you that this is a convex function. And on the other hand, okay, so if you fix beta, this is convex, so with the minus you get concave, so this is linear, so this is a concave function in theta. So it's concave in theta, and in beta it's linear, so it's convex actually. So linear, and so it's convex in the other variable. So I have a function of two variables, which if I fix one, it is concave. If I fix the other one, it's convex. And what you'd like to do is to show that you have this convex function in beta. So you're first, for each fixed theta, minimizing this convex function. And then once you minimize your convex function for each fixed theta, now you optimize over, so you maximize over your second parameter, which is theta, which is a concave function. And what you want to do is that the order in which you do that, it's not important. And this is because you have a convex concave function. Okay? So I'll show you how to prove that you can indeed exchange. These, but the reason is that one I just gave. You have a function of two variables, which is concave in one of the variables, convex in the other. Yeah.
Because in the second line, doesn't the beta that minimizes the expression use the minimum of f, or I'm missing something?
Sorry?
In the second line,
Yeah. The second line here. No, it might, well, it might be at the boundary of f. So you're not sure that the one which minimizes it's inside f. Yeah, but you could just, no, it doesn't depend on beta. What you don't understand? I don't, the beta which minimize this expression should be yes, that's if theta is positive, that's true. Yes. But mind that we'll take theta. Theta will belong to R, right? In this expression, it's finite for any theta. So indeed, for theta positive, that will be the minimum of f, and then for theta negative, it will be the maximum. Okay, so what I want to claim here is that I can exchange this infimum and then I have a definition for I. I of beta will be the supremum in theta in R of theta beta minus d log of m theta. And as I said, this is a convex function. Well, we will show. And so this is what's called the Legendre transform of the function log m. And this is a convex function. And it's also lower semi-continuous because for each fixed theta, this is linear function in beta, so it's a continuous function in beta. So if you take the supremum of continuous functions, you get a lower semi-continuous function. So this explains why I said that I, it's lower semi-continuous and convex. All right? So let me show that it's convex. So log of m theta, it's log of the expectation of the exponential theta x1. So let's take the first derivative of this function. So we get 1 over exponential theta x1 exponential x1 theta x1 and this is what I want to define as a new probability so in this space, in this probability space, which I started with, so I have in this probability space omega pf, we started with this probability space where these variables are defined. Now I want to define a new probability for each fixed theta. And this new probability for each fixed theta, it's defined by this formula. I'll go back to this in 1 second. Let me just conclude the computation of the derivatives of m. But then I'll go back to this observation because it's important to understand. So let me take the second derivative in theta. So we have, let me first take this derivative, and here I get exponent of x1 squared exponential theta x1 divided by the expectation of the exponential theta x1 minus, and when I take the derivative of the denominator, what I get is this is exponential x1 exponential theta x1 square divided by the exponential, the expectation of the exponential square. So with this notation, that would be the variance. So the expectation theta of x1 square minus the expectation theta of x1, and which is, well, strictly positive because this variance, it's 0 unless only if x1 is constant, which is not the case because x1 takes values 0 or 1 with positive probabilities. So this proves that the second derivative is strictly positive, which shows that log m it's indeed a strictly convex function. Okay, so we obtained the upper bound with this functional, which is the convex conjugate of log of m theta. These are called the convex conjugate. So you have a convex function, and its conjugate is given by this formula. And as I said, you can check that I, it's a convex function. So question about the upper bound. Okay, so the proof, it's quite straightforward. And realize essentially, as I said, you introduce an object which has expectation, which positive expectation equal to 1, depends on the parameter, and then you can just obtain the upper bound. So here I introduced this object, but the important fact is that Sn, it should be a function of x, n, of the variable which you are interested in. Fine. So this is the proof of the low bound. Later, or maybe tomorrow, I'll get to this proof. So now let me go to the lower bound. And for the lower bound, I want to investigate further this measure. Okay. So as I said, we are working in some probability space. And in this probability space, I have these variables, which under P are IID Bernoulli. Now I want to define a new measure, which is indexed by this theta, which belongs to R. And I'll say that, okay, what is the probability? These variables takes value 0, 1. So what is the probability under P theta that x1 takes some value z1, xn takes the value zn. So if I define that for all n and all sequence z1, zn, you can extend, and if these measures are compatible, you can extend this measure to the sigma algebra generated by x1, x2, xn. Okay. So I'll tell you what is this probability, and this is exactly by the one obtained by introducing these weights. So this is the expectation with respect to the original probability of the same event, that x1 it's equal to z1, xn it's equal to zn. And then I'll just repeat what we did. I'll get t exponential of theta, x sum of xj, so this is Sn. And, but okay, one way of writing it, it's so this is exponential. This exponential has mean 1. But another way into writing this, it's saying that this is the exponential, the expectation of this, of the probability of this event exponential theta Sn. And, well, this is a constant, so I'm multiplying it here, but there is a minus here, so this is divided by the exponential of n log of m theta. But what's log of m theta? So this denominator, I can write it as the exponential of log of m theta to the power n. And this is m theta to the power n. What is m theta to the power n? Is this expectation. So this is actually the expectation of x1 to the power n. Okay? So I can replace this exponential simply by the expectation of the exponential theta x1 to the power n. And this is what's appearing here. Okay? When n equal to 1, this gives me exactly the expectation theta of x1. All right? So this object is exactly the same as I defined here. Yes? No, z are numbers, 0, 1. These z1, zn are either 0 or 1. So these variables x1, xn, in this probability, they take only the value 0 and 1 with probability 1. So p theta does not change that. It changed the weight.
So, but in this case, wouldn't Sn be also constant because you're restricting the expectation that
It will be constant because I know exactly these values.
but you don't want to.
I don't want to. And I can, so and in this example, so everything I did here does not depend on the fact that these variables are Bernoulli. I just use independence, right? And the fact, and also that the expectation of theta x1 is well defined. Okay, but besides that, I didn't use anything. Okay. So what I want to compute is what is the distribution in our example of x1, xn. So what is this distribution? Okay, what is this probability? So what is the distribution of x1, x2, and so on under p theta? And for that, I will just compute. I'll continue this computation. As Thiago remarked, this computation is simple because now I can replace Sn by the sum of Zn, of the Zj, right? Here, that expression I can also compute, and this expression I can also compute. Okay? So, let me continue this computation. This is the expectation that x1 equal to z1, xn equal to zn. Now, I have the expectation of theta sum of zj. Remember that zj, it's either 0 or 1. And this is divided by the exponential of theta x1 to the power n. So what's the exponential of theta x1? Well, x1 takes the value 1 with probability alpha. So this is alpha exponential theta plus 1 minus alpha. And so this is equal, so that's exponential theta, let me call z bar, or z, the sum of zj. So this is exponential theta z. Now what is this probability? Well, this probability, these variables x1, x2 are independent, so this is equal to the product of probability that xj, but xj has the same distribution as x1. It's equal to zj. And this is divided by 1 minus alpha plus alpha exponential theta to the power n. Now, what is the probability that x1 is equal to zj? That is alpha to z1, zj. So if zj is equal to 1, this is alpha. And if zj is equal to 0, this is 1 minus alpha. Okay, so this is this product. Okay, let me continue the blackboard. So we have the exponential theta z, which is the sum of zj. Now we have alpha to the sum of zj, and 1 minus alpha to n minus the sum of zj. And this is divided by, okay. So maybe I will write this as 1 plus alpha exponential theta minus 1 to the power n. Okay? And what we get is that this is equal to the product from 1 to j of the exponential theta. So I have exponential theta zj, alpha zj, so this is alpha and 1 minus alpha, 1 minus zj. Okay. So what I claim is that this is exactly so what is the expectation under theta of x1? The expectation of x1 under theta, it's the probability that x1 is equal to 1 under theta. x1 takes only the value 0 and 1. And so by our formula, this is the expectation theta x1. And here we have the probability that x1 is equal to 1 exponential theta x1. So this is alpha e theta divided by 1 plus alpha sorry, 1 minus, so this is, what's this expectation? X1 takes the value 1 minus alpha plus alpha exponential theta. Okay, so let me call this maybe the mean in theta. So this is the expectation of m theta. And what I claim is that this is exactly equal to the product so of the same expression, so m theta z1, 1 minus m theta, 1 minus zj, sorry. So let's check that if I show that this identity holds, what I'm proving is that under theta, the variables x1, x2, xn are IID, Bernoulli, but now with the new parameter. Instead of having the parameter alpha, now they have as parameter m of theta. Okay, if you compute what is the probability that x1, xn, which are Bernoulli with parameter m theta, takes the value z1 up to zn, this is the formula you get. So if I can show that these two formulas, these two products are equal, what we get is that under the measure p theta, the variables x1, x2, and so on, they are independent, identically distributed, they are Bernoulli, but now the parameter is not alpha anymore, it's m of theta. So what this theta is doing is that it's exchanging the mean value of the Bernoulli variables. Okay, instead of having mean alpha, now you move the mean to this new value, which depends on theta. Is that clear? So remember, here I'm computing the probability under theta that x1 is equal to z1, xn it's equal to zn. And what I'm claiming is that what we obtain is this formula. And compare this formula with the formula. So let me go back here. Let me write here. What is, to remind you, what is the probability that x1 is equal to z1, xn is equal to zn? Well, we have seen that these variables are independent, so this is a product in J of the probability that xj is equal to zj. And they are identically distributed, and they are distributed according to a Bernoulli. So the probability that x1 is equal to zj, it's alpha zj times 1 minus alpha 1 minus zj. You agree? Okay, so this is what we get when the variables are independent Bernoulli with parameter alpha. But now I computed under this new probability the same event. And if I show that I have this identity, then I conclude, well, these variables, they are Bernoulli with independent Bernoulli with this parameter. Okay? And, okay, so let's show that these two so here is what m theta is. So this expression is actually equal to the product from 1 up to n. M theta is this expression, so this is alpha exponential theta 1 minus alpha plus alpha exponential theta to Zj. So this is m theta. And 1 minus m theta is the same expression in which I replace alpha exponential theta by 1 minus alpha. Okay, times 1 minus alpha, 1 minus alpha plus alpha exponential theta, 1 minus Zj. Okay, so this is equal to that expression. And now if I didn't do any mistake, what these two expressions should be equal to the same thing. So I'll put here Zj plus 1 minus Zj. I didn't do anything, right? And to write, so I have a piece which is alpha theta, or alpha exponential theta divided by this expression to the power Zj, which is this one, and then 1 minus alpha divided by the same thing to the power 1 minus Zj, which is the second. So these two expressions are indeed the same. Okay? So we just proved that, well, this measure which I just introduced in my space is very simple to interpret. Okay? So these variables under this measure, these variables are IID Bernoulli with parameter m of theta. Okay? And this is a function of theta. And I know that this function is increasing in theta, because this m theta is the derivative of log of m. Okay, remember that I had log of m, so taking the first derivative, which I computed here, log m of theta was the exponential of theta x1, and so the derivative of log of m theta, which I erased, was the expectation of x1 exponential x1 divided by x1, and this was the expectation theta of x1, and this is m of theta. Okay, so m of theta is the derivative of this convex function. And we proved that the second derivative is strictly positive, which means that the derivative of m is positive, which means that m is strictly increasing. Okay, so you have this function m of theta, which is written here explicitly. So it's increasing, and let's compute its limit. So it's defined for theta in R. So if I take theta to plus infinity of m theta, what do we get? Well, take theta to infinity, this is 1. And if you take theta to minus infinity, so you get 0. And these are all possible values. So you have m of theta, which is a function of theta, right? And if you send theta, it's increasing. If you send theta, so it's defined in R. If you send theta to infinity, it goes to 1. If you send theta to minus infinity, it goes to 0. So it looks like that. And so what it means that if I fix a density beta, I can find one and only one theta for which under this parameter theta, the average is beta. So this theta helps me to change, to modify the expectation of these variables, the mean of these variables. So did you understand? So what I did is that I introduced in my space a family of probabilities which depends on one parameter, theta. And what this parameter does, well, it changes the average of these variables. They are still independent, still identically distributed, but there is a difference. Their average is not alpha anymore, but it's something else. It's m of theta. But as I move theta, I can get all possible averages. If you tell me, well, I would like to have average 1/2, I can choose one and only one theta, which gives me average equal to 1/2. And mind that if I take theta equal to 0, then if I take theta equal to 0, this is 1. And what I get is that m of 0, it's alpha. So if I take theta equal to 0, well, that's natural, because if I take theta equal to 0, it's meaning that I'm multiplying by 1. So I'm not changing the measure. Okay? And this is the idea. The idea now is that suppose that you want the average to be equal to beta, which is different from alpha. So I want to compute what is the probability that xn bar is close to beta. So what I will do is that, well, I'll change the measure p to get the measure p theta, where theta is the parameter which gives me exactly the average beta. But there is a cost, because I'm changing the measure. And the cost will give me the large deviations, rate function I. So this is what I will do now. But before I do that, let me just, so we know exactly what p theta is. So p theta of f, let's say that now I take a function of f x1 xn. Instead of a probability, let me take an expectation with respect to theta. Okay. So by definition of E theta, it's you take the original E, you compute the expectation of x1 xn, and here you introduce exponential theta Sn minus n log m. Of theta. Okay, so this was the definition of my p theta, right? So, what is this? Well, this is the Radon-Nikodym derivative of d p theta n over dpt, dp, restricted to the sigma algebra of x1 xn. Okay? So this is exactly the formula of a Radon-Nikodym derivative. So remember, if I have an integral f with respect to d nu, and nu it's absolutely continuous with respect to d nu, I can, this is f d nu d nu d mu. All right? And so this is the Radon-Nikodym derivative of d nu with respect to mu. And so what is this formula? This formula, I'm integrating f with respect to p theta. And now I'm writing this expectation as equal to this expectation, but now I'm writing with respect to p. Okay. So what appears here, it's the Radon-Nikodym derivative of nu, which was this one, and mu. So the one which appears above, it's p theta dp. So this is actually the Radon-Nikodym derivative of p theta with respect to p. And this Radon-Nikodym derivative depends on how many variables you're looking at, right? Here I'm looking only the first n variables, because if I had here more variables, I would have to take here n plus 1, n plus 2, and so on. So this is why I'm saying that this is the Radon-Nikodym derivative restricted to this sigma algebra. Okay. So actually what's appearing here is that this Radon-Nikodym derivative. So now let's go to the lower bound. And the first observation is that p theta, under p theta, these random variables x1, x2, or iid, Bernoulli, but now with parameter m of theta. In particular, I have a law of large numbers. I know that under p theta, x n minus m theta larger than delta, that this limit as n goes to infinity, it's equal to 0 for all delta positive. So I have a law of large numbers for the perturbation. So I'll call these measures p theta the perturbation. And therefore I have a law of large number for the perturbations. Right? And now I can prove the lower bound. So I want the probability that xn bar belongs to an open set G. Okay. So let's take a beta which is in G. So fix a beta which is in G. Since G is an open set, there exists a delta such that B minus delta, B plus delta, it's contained in G. And therefore this probability, it's larger or equal than the probability that xn bar belongs to this set. So minus beta, it's smaller than delta. Okay? Now, so what's the problem here? The problem is that this measure is very small. Because if I take beta different from alpha, this is going to 0. So what I will do is I will make this event an event of probability 1. And how can I transform this event in an event of probability 1? Well, by changing p by p theta for a theta which is associated to beta. So I will find theta such that m of theta is equal to beta. And now I know that under theta, under this measure, xn, it's close to beta. So this event, it's now an event of probability 1 under this measure. So what I will do here is I will change this measure into the measure p theta. So how I do that? Well, I'll write this as p theta. Okay? But since this is p theta, I have to here pay a price, dp of the p theta, the Radon-Nikodym derivative, and then of the event xn bar minus beta is less than delta. And this is, let me call that Fn. So this is the Radon-Nikodym derivative of the first n terms. Okay, let me call that Fn. Okay, this event depends only on Fn, so I can take here the Radon-Nikodym derivative restricted to this sigma algebra. Okay, now this event has probability 1 with respect to this measure. But I had to pay a price, and the price is given by this Radon-Nikodym derivative. But this is the idea of the lower bound. So what you need in the lower bound is to find these perturbations which turn the event you are looking at a typical event, an event of probability 1. Of course, they may have many perturbations. You have to find the right one. All the other ones will give you too high cost to get that. So I computed here this Radon-Nikodym derivative, so the inverse is just 1 over that, 1 over this exponential. So this is the exponential minus of what's written there, which is theta Sn minus log m capital M of theta with an n. Right? Theta is n minus n log with a minus. Okay? So now, this is exponential. Let me put n. Now this becomes xn bar. Okay. Right? Now I know that xn bar belongs to this interval. Beta minus delta, beta plus delta. So I can bound this xn bar. So I want this to be larger. So I want xn bar to be smaller. So xn bar is smaller than b plus delta. Okay. Since xn bar is smaller than b plus delta in this event, so here I will replace xn bar by b plus delta, and I will get a lower bound. So I get the lower bound exponential minus n theta beta plus delta minus log of m theta. And then the probability over theta that x n bar minus beta, it's bounded by delta. Right? Okay. So again, what we proved is that this probability, it's bounded below by this expression. So if I take n, I take the logarithm, I divide that by n, what I get is that 1 over n log the probability that xn bar belongs to G, that this is larger or equal. So I'm taking the log and dividing by n, so I just get minus this expression, minus theta beta plus delta minus log of m of theta, and then plus 1 over n log the probability theta that x n bar minus beta is smaller than delta. Okay? That's fine, because now I can take the limit. So the first expression does not depend on n, and the second expression converges to 0, because I'm dividing by n, and this probability is converging to 1. So mind, actually, I didn't need really this event to have probability 1. It was enough to have a positive probability, because I'm taking the log and dividing by n. But the way in which you do it, you really make it to have probability 1. So since this converges to 1, this expression converges to 0. And so I get this bound. The left-hand side does not depend on delta, so now I can send delta to 0 to get that the limit inf of 1 over n log of the probability that xn bar belongs to G, that this is larger or equal than minus theta beta minus log of m theta. Okay? And there is nothing special about beta. Beta was any element of G. So I can now optimize over all beta. And since I'm taking low bound, I'll take a supremum over beta. With this minus, it becomes an infimum. Okay, so here is my bound. So this is exactly what I wanted to obtain. But here, maybe I got something different from I. So in the upper bound, I got I of beta, which was given by that formula. And now for the lower bound, I get this expression, where mind theta and beta are related by this identity. Okay? So here, theta, it's the one which it's related to beta by that. What I claim is that actually theta beta minus log m, it's exactly equal to I. So that this is equal to minus the infimum for beta in G of I of beta. So what I have to prove, it's I of beta, it's given by this. Okay? So what I have to prove is that the theta which maximizes this expression is the theta which satisfies this identity. Let's check that. So I of theta is given by that supremum. Okay. As I said, this is a convex function. So with the minus a concave, strictly concave. So the supremum will be satisfied by the singular point, which is beta minus. So I'm taking the derivative in theta of this expression and equaling that to 0. And this is times the derivative of log of m theta, that this has to be equal to 0. Okay? But the derivative of log of m, this is m theta. Okay? Remember that m theta was the derivative of log of m theta. So this is equal to m theta. And so the theta okay? So the theta which maximize, it's exactly given by this relation. And as I said, m is strictly increasing, so there is only one theta which satisfies this identity. And this was my point. You fix a density beta, then you find your parameter which gives you that density. And so I of beta, it's the one in which I take theta, it's equal to b theta minus log of m theta, provided I choose theta satisfying that. And this is exactly what we obtained here. Okay, so indeed I have I. And this proves, this completes the proof of the last deviation. Okay, we have the upper bound, lower bound. And well, and the cost was the cost of the Radon-Nikodym derivative. So this is giving me the cost, okay? Because I computed that, and around beta, I evaluated this cost, and this is exactly exponential minus n times e of beta, I of beta. Okay, so this is the proof, modulus the fact that we are able to replace sup and inf. So that I will show you tomorrow, and we'll start to prove the large deviations for the exclusion process. Okay, questions? Okay, so we stop here and we continue tomorrow with the exclusion.